In this video, we're going to go over the concept of bond polarity. Polarity is defined as the distribution of electrical charge between two atoms that are bonded together. When it comes to polarity, we must link it to electronegativity, which we observed before that it is a trend in the periodic table. To remind you, electronegativity is a measure of the tendency of an atom to attract electrons. This unit has, or this value, I should say, has no units. It's just based on the Pauling scale. So the majority of the elements in the periodic table are going to have an assigned number in this scale. We can observe in the periodic table that we have on slide 8 that we have the different electronegativity values for a number of elements in the periodic table. To remind you, the most electronegative atom in the periodic table is fluorine. In the periodic table, the trend for electronegativity is that when we move across a period from left to right, we see that the values of electronegativity are going to increase. Additionally, as we move up in a group, also the electronegativity values are going to increase. Using electronegativity values, we can actually define the type of bond that we have in a molecule. And it is important to note that there's going to be different types of bond, starting with a nonpolar covalent bond. When two atoms are bonded together and they're sharing electrons, a nonpolar covalent bond is going to illustrate a type of covalent bond in which the bonding pair of electrons are equally shared by the bonded atoms. Not all molecules have nonpolar covalent bonds. At times, we see molecules that has great differences in their electronegativity, meaning that we are going to see that one atom is going to have a larger value for electronegativity, and the result of this is going to be bond polarization. In bond polarization, all we're trying to illustrate is that if we have a difference between the electronegativity of two atoms that are bonded, then all of a sudden, because there's going to be one side that has a higher electronegativity value, this means that electron density will be specifically pulled more towards it. To look at bond polarization, let's look at figure 5.7. So I'm zooming in on the left side of the slide. Here we have a molecule that is HF. This is hydrogen monofluoride. If I assign the electronegativity values for hydrogen and fluorine, we see that hydrogen, based on the values that we have in the periodic table in the previous slide, it has an electronegativity value of 2.1. Fluorine, on the other hand, has an electronegativity value of 4.0. The back heat map that we have is going to show us the greater electron density that we have in this molecule. The blue color represents less electron density, while the red color represents higher electron density. We can observe that around fluorine, because it's more electronegative, there's going to be higher electron density. In this molecule, since there is an electronegativity value difference, which means that fluorine is more electronegative than hydrogen, then we see bond polarization. This bond polarization can be illustrated with different symbols. The symbols include partial charges, And whenever we have a partial charge, you see the symbol delta, which is this S looking symbol that you see right here. And since fluorine is more electronegative than hydrogen, fluorine gets a partial negative charge, and we write it as delta minus. Since hydrogen has a less electronegativity value, then we put on it as a sign a partial positive charge. Additionally, vector arrows can be utilized to show bond polarization. And what we observe is that when we draw the vector arrow, the tip of my vector arrow is going to be pointing towards the most electronegative atom in the molecule. Because of bond polarization, we have an additional type of covalent bond, which is called a polar covalent bond. And when it comes to this, remember that polar covalent bonds are due to polarization, and it is because when it comes to the electron pull, since we have a great difference of electronegativity values between the two bonded atoms in the molecule, this polarity actually comes in because the electrons are not shared equally. In this textbook, when it comes to classification of bonds, we actually have in figure 5.1 the distribution for looking at all the type of bonds that may exist in different molecules. We can see that the three main types of bonds that can exist in molecules overall are nonpolar covalent bonds, polar covalent bonds, and lastly, ionic bonds. So if we look at the electronegativity difference of two molecules, we can utilize the distribution in figure 5.1 to define what kind of bond actually is present in a molecule. According to the rules in this textbook, if you have two atoms bonded together, but when you look at their electronegativity difference, which is symbolized by this triangle, capital E, capital N, which is just means delta and En. When that electronegativity difference is zero, then we have a pure covalent bond. In other words, we have a non-polar covalent bond. And any difference in electronegativity, meaning that we're going to just subtract those values, that it is less than 0.4 is going to refer to nonpolar covalent bonds. If the difference, meaning the subtraction of the two values, lands between 0.4 to 1.8, then those bonds are considered polar covalent bonds. Any two atoms that have an electronegativity difference of 1.8 or higher are considered purely ionic bonds, meaning that the electrons in these atoms are going to either fully lost or fully gain instead of being shared. Only covalent bonds, polar or nonpolar, are the ones that are sharing electrons. In order to solidify this concept, let's do some practice problems. In these practice problems, in Roman numeral 1, the instructions basically say that we're going to look at the electronegativity value for each of the atoms, and then we're going to illustrate bond polarization. Let me remind you, bond polarization can only be used in bonds that are polar covalent. Let's look at letter A, in which we have iodine and chlorine. I'm going to first assign the electronegativity value for both atoms. When I look at the periodic table that is on the right side of the slide, I'm going to search for iodine, which specifically is right here. And I can observe that it has an electronegativity value of 2 0.5. Next, I search for chlorine. Chlorine lives here, and it has an electronegativity value of 3.0. When I'm trying to calculate electronegativity difference, I'm just going to subtract the larger value by the smaller one. So if I subtract 3.0 from 2.5, the electronegativity difference is going to equal 0.5. When you have an electronegativity difference of 0.5, this means that this is going to be specifically, according to the distribution that we have here, a polar covalent bond. Since we have a polar covalent bond, then we can illustrate bond polarization. Since chlorine is more electronegative, then we can do a vector arrow in which the vector arrow is going to be pointing towards chlorine, since it is the most electronegative atom. Additionally, we can use the partial charge symbols. Since chlorine is more electronegative, I'm going to use a delta minus sign. Since iodine is less electronegative than chlorine, we're going to do a delta plus sign. Now let's do example B. We have bromine and bromine. When I look specifically at the electronegativity value for bromine, it is right here. It is 2.8. So each bromine get an electronegativity value assigned of 2.8. When I look at the difference in electronegativity, that difference in electronegativity is 0. Anything that has an electronegativity value that is less than 0.4, it is considered a nonpolar covalent bond. In a nonpolar covalent bond, we cannot use any of this signage because those signs are exclusively utilized for polar covalent bonds. Let's now move to Roman numeral 2. In Roman numeral 2, we are given different molecules. And in those compounds, we just have to determine what kind of bonds are present in it. Similar to the practice problem in Roman numeral 1, we're going to assign the electronegativity values for each of the atoms in this molecule. In letter A, we have a molecule that is only 2 atoms, chlorine and fluorine. So when it comes to this is just uh, allowing us to look at the electronegativity value for each of those atoms. Chlorine has electronegativity value of 3.0. Fluorine has an electronegativity value of 4.0. When it comes to the difference in electronegativity, because it is 1.0, this represents specifically a polar covalent bond because the values are between 0.4 and 1.8. So when we classify the bond that allows chlorine and fluorine to come together, this is going to be a polar covalent bond. Let's look at magnesium and oxygen. Magnesium and oxygen, when I assign the electronegativity values, magnesium has an electronegativity value of 1.2. Oxygen has an electronegativity value of 3.5. So the difference in electronegativity for these molecules is 2.3. So that means that when I look at my distribution, since 2.3 is on this range, that means that for magnesium and oxygen, the type of bond that is present in this molecule is going to be an ionic bond. We can see that in the next example, we have Pi3. That means that phosphorus is in the middle and is surrounded by iodines. So essentially, In order to categorize the type of bonds in this molecule, we're going to look specifically at the electronegativity difference between phosphorus and iodine. Phosphorus has an electronegativity value of 2.1. Iodine has an electronegative value of 2.5. The difference in electronegativity is actually 0.4. And according to the rules, at specifically 0.4, we are going to consider this. So if you're exactly at 0.4, that's going to be considered a polar covalent bond.